Let's now work an example of computing the complex Fourier series of a square wave. So here's our function. It is symmetric about 0, 50% duty, going from +1 to -1, and it has a period of t, capital T. So we need to compute the Fourier series over any period t. So we could compute it from time 0 to capital T. We could also compute it from -t/2 to t/2, and that's what I'm going to do here. So we have f of t is going to be equal to +1 for time between 0 and t, and it'll be -1 from, I'm sorry, to t/2, -1 from -t/2 to 0. So this is just defining it for one period. This is the period over which we're going to compute the complex Fourier series. So f of n is equal to 1 over capital T integral from -t/2 to t/2. Our function f of t e to the -jn omega naught t dt, where omega naught is 2 pi over capital T. We'll split this integral into the two pieces. We'll go from -t/2 to 0, and there the function has a value of -1. Plus 1 over capital T integral from 0 to capital T/2 of +1 times e to the -jn omega naught t. So here we'll have a -1 over capital T. Take the integral of the complex exponent, and we get 1 over -jn omega naught times, and then we will have e to the 0, which is going to be 1, minus e to the jn omega naught, which is 2 pi over t times capital T/2. So I've combined the two negatives there. Our second term will be +1 over capital T times 1 over -jn omega naught times, and then here we will have e to the -jn 2 pi over t times t/2 minus be 1 when we evaluate the complex exponential at time 0. So this will give us, let's see, the omega naught is 2 pi over t, so we'll have -j over 2 pi n times 1, and this will be minus e to the jn pi plus j times 1 over 2 pi n quantity e to the minus, did I lose a sign? Okay, e to the minus jn pi minus 1. Now we need to note, what does this e to the jn pi evaluate to? So think of the unit circle on the complex plane. We have the real and the imaginary, and jn pi will lie, if it's even, it's going to lie right here. So this is going to be n even, and if it's odd, like j1 pi or j3 pi, it'll lie over here, and odd. And this is plus 1. And this ends up being minus 1. And the same is true for this second term here. Doesn't matter which way you go around the circle, it'll be the same case. So we can write that as actually, let's do this. We'll make this plus, we'll make this minus, and then we can combine. We'll go 1 over 2 pi n j. We'll combine the two minus 1's to get minus 2, and then here we'll have 2e to the j n pi, where we've recognized that e to the minus j n pi gives the same values as e to the plus j n pi for integer values of n. So this gives us j over n pi times e to the j n pi minus 1, and this evaluates to, this right here is going to be plus 1 when n is even, and minus 1 when n is odd, which means that this will be equal to 0 for n even, and it will be minus j2 over n pi when n is odd. So we can draw the frequency spectrum, say n, and let's plot the magnitude of f of n. So it is 0 for all, let's see, 1, 2, 3, 4, 5, 6. It's 0 for all even values. 1, 2, 1 minus 3 minus 5. Okay, and then it's going to be 2 over pi, 2 over pi for, say this is n, yeah, for, I'm going to drop off the omega here, but it's n omega naught. Okay, 2 over pi. Then it will be 2/3, 2 over 3 pi, sorry. 2 over 3 pi. Then 2 over 5 pi. 2 over 5 pi, and etc. Okay, that's the magnitude, and then what's the argument? The angle is going to be 1, 2, 3, 4, 5, 6. So we'll only plot it for the odd values. 1, 3, 5, minus 1, minus 3, minus 5. In each case, the coefficient is purely imaginary. It is always sitting around the complex plane. It is always pointing down. Okay, and the value that it points to is minus 2 over n pi. The angle never changes. The angle is always minus 90 degrees. So it'll just be minus 90. Take that back. It's, remember, the angle of f of n is an odd function, right? So when we plug in minus 1, we will get, it'll point up here, it's going to be this direction for n greater than 0, and it'll be pointing this direction for n less than 0. Okay, this will be pi over 2 minus pi over 2, or 90 degrees minus 90 degrees. Here's a MathCad animation that shows the reconstruction of the square wave by using the result that we found right here. And I made this little animation, where we are going to vary the number of terms that we're going to add. So up here, where it says n equal frame equal, that's the number of terms. So 1 is just the fundamental. Now we add a second term, but the second term, the even terms, are 0, so that doesn't do anything. We add a third term. Then we add fourth term, which is 0, fifth term, seventh term, 9, 11, and on up to 15. Okay, and you can see that as we add more and more terms, the square wave begins to take shape. Now, we expressed this this f of t, or f hat of t, by summing complex exponentials. Now we can do this also by directly summing sines and cosines. I'm going to show you how this relates back to the trigonometric Fourier series. But what we'll do is actually we're going to find the complex Fourier series coefficients, f of n, and then instead of writing, reconstructing our signal using the complex exponentials, we'll use f of n in a trigonometric term that involves just a cosine or sine of omega, or n omega t. So here's our reconstructed f hat of t, and we're going to rewrite the sum. Instead of being from negative infinity to the infinity, we'll write it. We'll write a 0th term, and then we'll go from n equal 1 to infinity, and we'll sum two terms: f of minus n e to the minus j n omega naught t plus f of n e to the j n omega naught t. Okay, so these are equal. We've just limited the sum and put two terms in there to capture the negative terms. Now recall that since the argument of f of n is an odd function, and the magnitude of f of n is an even function, we can write that f of minus n is equal to the complex conjugate of f of n. So we can use that in our summation above. We will have summation from n equal 1 to infinity, and here we will put f n star e to the minus j n omega naught t plus f of n e to the plus j n omega naught t. Now we can represent f of n in polar form as a magnitude times an angle, which we can either write as f of, angle of f of n, or arg of f of n, or we'll write it as the magnitude times e to the j angle of f of n. All right? And f of minus n is equal to f of n complex conjugate, which can be written as the magnitude of f of n times e to the minus j angle of f of n. Now we'll use those expressions above. Clear this out. So let's rewrite f hat of t equal to f naught plus the sum from n of 1 to infinity, and we're going to put f of n times the quantity, and then we'll have e to this. I'm going to do this term here first. We'll have e to the j n omega naught t times e to the j angle f of n. And we can actually combine those together. So I can actually remove that, and we'll write it as e to the j n omega naught t plus angle of f of n plus e to the minus j n omega naught t plus angle of f of n. Okay, and now what we recognize is that this term here is equal to 2 times the cosine of n omega naught t plus the angle of f of n. Okay, so we can therefore write that f hat of t is equal to a possible DC term plus a sum of cosine terms, 2 times the magnitude f of n times cosine n omega naught t plus the angle of f of n. Let's check that out for our example above. We found that f of n was equal to 0 when n was even, and we found, what was it, minus j2 over n pi when n was odd. So we can write f hat is equal to the sum from n equal 1, 3, 5, etc. of, let's say, 4 over 2 pi, 4 over n pi, okay, times the cosine of n omega naught t plus, and remember the angle, in all cases the angle was minus 90 degrees, okay, minus pi over 4, which this is equal to the sine of n omega naught t. So therefore we have f hat of t is equal to all of the odd terms of 4 over n pi sine of n omega naught t. Okay, and here we have I have a MathCad expression of this here to show that in fact it does reconstruct it. So let me stick it in here. Okay, so notice I have the 4 over pi, 4 over n pi, and this term here is just ensuring that this implements the odd n right here. And this is for a period of 15 terms. Okay, so this is an alternative representation of the reconstruction of your complex Fourier series of f of t using just trigonometric functions.